In my job, I ask questions for a living. And the question that is currently keeping me busy is who put that plastic into our water? And that might seem like a silly question because, we all know that there are a lot of things made from plastic and a lot of them can end up in the environment. And you've probably even heard of microplastics, these like tiny, tiny pieces of plastics that are absolutely everywhere in the environment. But once these things are in the environment, it's impossible to figure out what plastic they came from to begin with, right? Or is it? Thank you all for joining me for my talk. I'm so excited to be here. And as Sarah was saying, so my name is Roxana Suehring. I'm an assistant professor at Ryerson University, and I'm an environmental analytical chemist who studies different plastic contaminants in the environment. And I'm going to tell you more what that actually means. But I wanted to start off with a quick question for all of you. If you look around your room right now, what's your guess? How many things plastic do you have in your room right now? That's the thing, we use a lot of plastic in our everyday lives, right? So actually, if you look at an average North American or European person, we use actually around 100 kilograms or 220 pounds of plastic each year. Mostly that's packaging and wrapping. So that's, when you calculate that down, around a pound of plastic per family per day that we're using. And a lot of these plastics are actually single-use plastics. So they are, like your little cellophane wrapping or your, single-use plastic bag that you will use once, as it says on the tag, and then you basically throw it away and it becomes garbage. And of all of this plastic that we're using, actually only about 10% gets recycled. And the rest, depending on where you live, either gets incinerated, so it gets burned, or it ends up in landfills, or quite a bit of it might not ever make it into the waste stream at all and just end up in the environment because of littering or because the raccoons have taken it out of your garbage bin. So now, is this a problem? I mean, obviously none of us like plastic garbage in the streets, right? But the thing is actually with plastic, it doesn't disappear once it gets into the environment. So it doesn't degrade, it isn't broken down, it actually just turns into smaller and smaller and smaller and smaller pieces, up to the point where it becomes a so-called microplastic. And so microplastics are tiny pieces of plastic defined by being smaller than 5 millimeter. And so, let's see if you can see this. But so if you look at this, there's a tiny, tiny scale down at the bottom here. And if you see about the size of my little finger here, that's 10 millimeter. So it's, 10 millimeter, 5 millimeter, it's tiny. That's the largest pieces of plastic that count as a microplastic. So, and what happens to these tiny, tiny pieces of plastic? They can end up then in our water, they can end up in our air, they can end up in our food, and eventually get into animals' bodies out in the environment, for example, fish that we might be eating then, so they can end up in our body or in our drinking water. And that can actually really be a problem for our and animals' health, because our bodies were not designed to have plastics in them and digest plastics. And plastics actually can contain other chemicals that can be a potential health problem. And I'll tell you a bit more about that later. So, but when I then say specifically about water, so when you think about a plastic water bottle, any plastic water bottle has on average around 300 microplastic particles per liter in it. So here, if you look at this is now obviously not microplastic, but just give you a bit of a feel. So in here, that would be about how many particles in terms of microplastic particles you have in any given plastic water bottle. And this can actually get up to over 10,000 particles. So the question is really, would you drink this if you knew that there's that much plastic in there? And so that's for just the human side. But actually in the ocean, there have been estimates that by 2050, there will be more plastic in the ocean by mass than fish. And all of this plastic, and these are larger plastic items obviously as well, but they will all eventually break down to these tiny, tiny, tiny microplastics, which means they can get back into, the food cycle. But also it's really difficult to clean up because you have just millions of these tiny, tiny particles. So now the thing is, what can we do about this? And here you probably think I'm going to give you the speech about that you should be doing more recycling and that you should be using less plastic and that you should be more careful about what you do with your waste. And, don't get me wrong, recycling is great. It's a great idea. But it's actually not your fault that the recycling rate is so low. And it's not because you didn't separate your waste properly or you didn't, wash your takeout containers. The fact is actually that for most plastics, it's cheaper to just make new plastics than to recycle them. And that means that for most plastics, the industry isn't even trying to recycle because it's just not economically profitable, feasible. So at this point, recycling is really not, a solution to this problem, even if all of us we're super careful with how we separate our waste and wash our takeout containers and so on. So what can we do then if recycling isn't the solution, at least now? And from a scientific point of view, one of the most important things is actually to try and figure out where all of this plastic comes from to start off with. Because, if we don't know where all of these tiny plastic particles actually get into our environment, there's really not that much that we can do about it. So, and this is where it gets really interesting, but also really complicated. Because the thing is that a plastic isn't a plastic. So just to give you an example, I have here my phone made out of plastic, and I have a rubber duck. So both of them are made out of plastic, but this is pretty much where the similarities end, right? So what are a couple of differences you see between the two of them, phone versus rubber duck? So for example, if you look at the rubber duck is kind of squishy. It's bright red with like white thing. One of them will float. The other one I probably shouldn't put into water. Exactly. So also, if I throw this thing against the wall, it doesn't really bother the duck, right? I'm just not gonna showcase that with my phone. So there is clearly a resistance, for example, in terms of the properties. The phone is probably more brittle in terms of the plastic. The screen will just crack and break. So the thing is that all of these differences are what I would call properties. And these properties are introduced to this product, the phone versus the duck, by using different types of plastics, but particularly also by using different chemical additives. For example, you can use plasticizers to make the rubber duck squishy and easy to manipulate. You can use flame retardants, so-called flame retardants in a phone that will make it more resistant to burning, which is what you want with electronics that can get hot. You have obviously different dyes in there just to give them the different colors. And so the interesting thing from a chemistry point of view is that these types of additives are really quite specific for the type of product you have, plastic product. So the rubber duck, for example, doesn't need to have flame retardants in it. It's probably in the water and it should be in contact with a heat source. Whereas the phone, for example, doesn't need to be squishy, And so these different chemicals can actually be used to identify the type of product that these plastic particles came from. If the phone and the rubber duck later on went into the waste, broke down into little microplastics, and unfortunately made it to the environment. And so what we use there is really that we create fingerprints for the different products, plastic products, using chemistry, analytical chemistry, to figure out, in here in Toronto, in this specific river, where did the different types of microplastics actually come from? What type of products polluted this river with plastics? But the problem is that each one of these products obviously doesn't just contain one or two plastic additives. They contain hundreds or sometimes even thousands different types of chemicals. Some of them plastic additives, some of them other things. So what we do is that we use machine learning, so computer programs, artificial intelligence, to actually pick out what combination of different additives and chemicals within any given product is really specific and indicative for that product. So what allows us to identify the phone versus the rubber duck once it's in the environment. And now the question is, what are we actually hoping to achieve with all of this in the end? So as I said before, knowing where the plastic comes from is actually really helpful to figure out what to do about it. So we can help regulators, for example. If we figure out that there are local plastic producers and the plastics in the water come from them, they can step in and say, okay, please clean up your wastewater. But it can also help with, optimizing water filtration for the specific types of microplastics that are found in a local environment to keep, people in the environment safe. But it can also, and I think this is actually a quite important point, it can help every one of us to identify and find solutions to reduce plastics in the environment that we are actually personally responsible for. So a lot of plastics in cities particularly actually are fibers. So they are little pieces of clothes that come out of our laundry when we wash our clothes. And there are easy solutions for this. There are lint filters that can be installed. There are little catchers called, for example, Cura balls. And all of these are quite cheap. They're usually like less than 20 bucks, often less than 10 bucks. They're reusable and easy to install. Then obviously there are plastic bags, for example, single-use plastic bags that can be replaced by paper bags or multi-use bags. And these are just a couple of examples. It's quite, if you just Google plastic-free living or reducing plastic, there are lots of inspiration of what you can do to reduce how much plastic you're using. But honestly, I think the most important thing is actually just to not use plastics as a default, but to actually think, do I really need to wrap this in plastic? Or, could I put it into a glass container, for example, for food? Do I need kitchen utensils out of plastic, or can I use wood? What about clothes? Does there need to be polyester in there, or do I use full cotton or wool? What are other alternative materials? And you as a consumer actually have a lot of power. So you can ask for plastic-free products. You can also use for reusable items instead of single-use. And really importantly, circling back to this recycling thing, you can actually demand for recyclable items to push for more recycling by the industry. And then at some point, I might actually not have to be a plastic detective anymore, and will then move on to other fascinating questions, because that's the beauty of science. There are always more questions to ask. And I hope you have lots of questions for me. So these are chemical fingerprints. So they are not actually a human fingerprint, but basically this combination of additives that I mentioned. So for example, in the rubber duck, to make it squishy, you will have plasticizers in there, different types of plasticizers. It was also bright red. That means there is a red dye in there. There's also a white dye in there. It had like this little white cross. And so then in the polymers, so the plastics themselves, the different spacers, it will be different types of plastic actually. And all of this information together makes basically the chemical fingerprint of that specific rubber duck. And since, you know, a lot of these rubber ducks will have a quite similar type of fingerprint, we can basically relate it back to that type of product. No, I don't think so. Plastic, and I honestly, it's also, I don't think we need to go that far. So I think there is, you know, plastic isn't like this absolutely enemy material that we shouldn't be using at all anywhere ever in our lives. Plastic has revolutionized a lot of things we're doing, and there are a lot of applications where, you know, plastic is really the best option if you put, you know, even from an environmental point of view. And, you know, there is movement now also into more biodegradable plastics, even though we are right now not quite there yet. Most things that are where it says biodegradable plastic actually don't necessarily biodegrade. But so the thing is really right now, I think there is an overuse of plastic, and particularly also a waste mismanagement. And that has led to having all of this plastic pollution in the environment, which clearly is a problem. But I don't think, you know, we need to go all the way the other way now and say we're never going to touch plastic again. Yeah, super scary study, definitely. So, and that's the thing, right? Like a lot of very, very tiny plastics. So when I showed you like the you know, the scale, these were the largest microplastics you can find that are still defined as microplastics. Quite a few of the plastics actually are in the nanoscale, so they aren't even visible anymore to just the naked eye, right? And often, some of these plastics, at least, tiny particles, can actually get through even membranes in our bodies. They can get into different organs and so on. And as it looks now, even all the way into the human placenta. And this, you know, we don't know yet whether plastics within the human placenta, for example, might be a problem for the developing, you know, fetus. The science is really young there in that sense in terms of potential impacts. But, you know, at the end of the day, I'd rather there isn't any plastic there. Well, yeah, and that's the thing. So first of all, particularly these really small plastics, they are in practically any fish you might eat, any food item will have tiny, tiny plastics in them. So then you will ingest them through that, just through the food you're eating. And then, you know, the bottle I showed. So on average, any plastic bottle that you drink out of has over 300 particles that you will just be drinking. That will just get into your body. And some of them have over 10,000. So they will just be in your stomach after that. But then even some of the plastics, they are so small and light that they're even in the air we breathe, in the dust. So they can get into our lungs, for example, as well. So there are various ways of how it can enter our bodies. Yeah, no, absolutely. So there are different ways of doing this. So often bioplastics are, for example, so a normal plastic, a non-bioplastic, this is basically made out of oil. So plastics are as much a product of, fossil fuels as, your gasoline, for example. It's just a different way of processing this oil to make plastic. So, and this is also one of the reasons that it is really quite stable in the environment. And bioplastics basically uses other types of materials, other types of basic chemical structures to basically get a similar material. So, for example, you can use chitin, like the stuff that shrimp, bodies are made of. You can make polymers and plastic basically out of that. You can use the stuff that's in eggshells. Like there's a variety of different, basically products that will just degrade in the environment because, they are meant to break down and be eaten by microbes and so on. But a lot of times the problem with those ones is that are really well biodegradable, that they will basically degrade too quickly for, to have the same use as your, fossil fuel based plastic. And so then what happens is that you have combinations of the more bio and more fossil fuel plastics, or you treat the more bioplastics to a way to make them durable, which then makes them not break down again. So that's a little bit of the fine line that people are walking right now, where they are trying to develop more degradable bioplastics, which I think is a great way forward, but that still lasts long enough, that you can carry your grocery home.